We have a name for them: black holes. The word itself conjures images of the ultimate cosmic monster, a gravitational abyss from which nothing, not even light, can escape. We think of them as the great destroyers, the silent, invisible predators that roam the cosmos, devouring stars and swallowing worlds. And in a sense, this is true, but it is not the whole truth. What if I told you that these cosmic monsters are also the great architects of the universe? That the supermassive black holes that lurk at the hearts of galaxies are not just agents of destruction, but are also the hidden sculptors of creation. Tonight we journey to the heart of the galaxy to explore this profound and beautiful paradox. We will discover how these gravitational titans regulate the birth of stars, and how they may be the very reason that galaxies, and therefore we, exist at all. Prepare to see the monster in a new light. Prepare to meet the hidden architect of the cosmos. Before we can understand how a black hole can shape a galaxy, we must first appreciate the sheer scale and power of the objects we are dealing with. For most of the 20th century, black holes were a purely theoretical curiosity, a strange and unsettling prediction of Einstein's theory of general relativity. But in the 1960s, astronomers began to discover a new class of object that defied all known physics. These were the quasars. They appeared as faint, star-like points of light in our telescopes, but their light was incredibly redshifted, meaning they were among the most distant and most luminous objects in the entire universe. A single quasar could be brighter than 1,000,000,000,000 suns, outshining its entire host galaxy by a factor of 100. What could possibly be powerful enough to generate this much energy in a volume of space no larger than our own solar system? The answer, theorists proposed, had to be a black hole. Not the small, stellar mass black holes left behind by a single dead star, but a new class of monster altogether, a supermassive black hole with the mass of millions or even billions of suns. The theory was elegant and compelling. As a supermassive black hole fed on the gas and dust at the center of a young galaxy, this material would form a swirling, superheated accretion disk, releasing a colossal amount of energy in the form of light. The quasar was not the black hole itself, but the brilliant, violent death cry of the matter it was consuming. For decades, this remained our best, but still indirect, evidence for these cosmic titans. To truly prove that a supermassive black hole was real, we would need to find one that was not actively feeding, a quiet, dormant monster in a nearby galaxy. We would need to see its gravitational influence directly. We would need to go ghost hunting. And the most logical place to hunt for such a ghost was at the very heart of our own home galaxy, the Milky Way. The center of our galaxy, located about 26,000 light-years away in the direction of the constellation Sagittarius, is a place of extreme crowding and is completely obscured from our view in visible light by thick clouds of interstellar dust. But in the infrared and radio parts of the spectrum, we can peer through this dust and see the stars at the galactic core. In the late 1990s, two independent teams of astronomers, one led by Reinhard Genzel in Germany and the other by Andrea Ghez in the United States, began the most patient and painstaking astronomical survey ever conducted. For over 2 decades, they used the world's most powerful telescopes to take sharp, high-resolution images of the very center of our galaxy, year after year. Their goal was to track the precise movements of the individual stars that were orbiting the galactic heart. And what they found was a stunning and beautiful confirmation of Einstein's theories. They found a swarm of stars, which they named the S-stars, that were whipping around an unseen central point at incredible speeds. One of these stars, S2, completes a full orbit every 16 years. At its closest approach, it travels at over 25 million kilometers per hour, or about 3% of the speed of light. These stars were performing a frantic, high-speed gravitational dance around a partner that was completely and utterly invisible. By precisely mapping the orbits of these S-stars, and by using the simple, elegant laws of gravity first laid down by Johannes Kepler, the two teams were able to calculate the mass of the unseen object that the stars were orbiting. The answer was unambiguous. The central object had a mass of about 4 million times the mass of our Sun, and all of this mass was packed into a region of space smaller than the orbit of our innermost planet, Mercury. There is only one object in the universe that can be that massive and that compact. It had to be a supermassive black hole. This was the smoking gun. For their decades of meticulous, patient, and groundbreaking work, Genzel and Ghez were awarded the Nobel Prize in Physics in 2020. They had given us our first, direct, and undeniable proof that the monsters in the middle were real, and our own galaxy had one, a quiet, sleeping dragon at its heart, an object we call Sagittarius A star. The confirmation of a supermassive black hole at the heart of our own galaxy, and the subsequent discovery that nearly every large galaxy we look at has one, opened up an entirely new field of astrophysics. But it also presented us with a profound and deeply puzzling mystery, a cosmic chicken and egg problem that we are still struggling to solve. The mystery is this: the mass of a supermassive black hole is not random. It is intimately and inexplicably linked to the properties of the galaxy it lives in. As astronomers began to measure the masses of supermassive black holes in dozens of other galaxies, they noticed a startling and beautiful correlation. They found that the more massive a galaxy's central bulge, the dense spheroidal component of stars at its heart, the more massive the supermassive black hole at its center. This tight linear relationship is known as the M-sigma relation. It is one of the most fundamental and most surprising discoveries in all of galactic astronomy. To understand why this is so surprising, we must again consider the question of scale. A supermassive black hole, while incredibly massive, is also incredibly small. The event horizon of our own Sagittarius A star, with a mass of 4 million suns, is only about 24 million kilometers across. It could fit comfortably inside the orbit of Mercury. The central bulge of the Milky Way, on the other hand, is a colossal structure, thousands of light years in diameter. This means that the black hole is 1 trillion times smaller than the galactic bulge it is connected to. The direct gravitational influence of the black hole is limited to only the very innermost few light years of the galaxy. It has no direct way of affecting the growth of the vast, sprawling bulge of stars that is thousands of light years away. And yet, the two seem to know about each other. They seem to have grown in perfect lockstep, as if connected by some invisible galactic-scale communication system. It's like discovering that every tree in a forest has a root system whose mass is always exactly 1,000th of the mass of its branches. It would be an uncanny and deeply meaningful correlation that would tell you that the growth of the roots and the growth of the branches are not independent processes, but are part of a single, self-regulating system. The M-sigma relation is the same kind of clue. It is telling us that the growth of a galaxy and the growth of its central black hole are intimately connected. This is the great coevolution problem. This discovery raises a profound question of origins. Which came first? Did the galaxy form first, and its properties then determine how large a black hole it could grow at its center? Or did the black hole form first, a massive primordial seed in the early universe, which then acted as a gravitational anchor around which the galaxy grew? Or, in the most likely and most complex scenario, did the two somehow grow together, locked in a delicate and violent feedback loop where each one's growth influenced and regulated the growth of the other? The M-sigma relation is a fossil record of this coevolutionary dance. It is the end result of a multi-billion-year-long conversation between a galaxy and its central monster. To understand this relationship, to solve this cosmic chicken and egg problem, we must understand the language of that conversation. We must understand how a tiny, invisible black hole can reach out across thousands of light years and influence the growth of its entire host galaxy. And the answer lies in the incredible galaxy-shaping power that is unleashed when the sleeping monster awakens and begins to feed. A dormant black hole, like the one at the center of our own galaxy today, is a quiet and stealthy creature. It is a pure gravitational entity, its presence felt only by the stars that orbit it. But when a supply of fresh fuel, a cloud of cold gas, a dust lane, or an unlucky star wanders too close, the sleeping monster awakens. And in its awakening, it unleashes the most powerful and most luminous engine in the entire known universe. This engine is the accretion disk. The accretion disk is the source of all of a black hole's creative and destructive power. It is the mechanism by which a tiny, invisible object can project its influence across an entire galaxy. To understand how black holes shape the cosmos, we must first understand the violent and beautiful physics of this cosmic whirlpool. The matter that falls towards a black hole rarely falls straight in. It almost always has some amount of sideways motion, some angular momentum. This means that as it is pulled inward by the black hole's gravity, it does not fall directly to the event horizon. Instead, it is forced into an orbit. A vast, flat, and rapidly spinning disk of material forms around the black hole, much like the rings of Saturn or the protoplanetary disk around a young star. This is the accretion disk. But an accretion disk is a far more violent and energetic place than Saturn's rings. The material within it, gas, dust, and the shredded remains of stars is orbiting the black hole at incredible relativistic speeds. The material in the inner parts of the disk is moving much faster than the material in the outer parts. This difference in speed creates an immense amount of friction. The layers of the disk rub against each other, and this friction generates a colossal amount of heat. The accretion disk is heated to temperatures of millions or even tens of millions of degrees Celsius. It becomes a swirling, incandescent inferno of plasma, hotter than the core of the most massive star. It is this intense heat, generated by friction, that causes the disk to shine with a brilliant, ferocious light. This is the engine of a quasar. It is crucial to understand that the light is not coming from the black hole itself. The black hole is still perfectly black. The light is coming from the matter that is just outside the event horizon, in the final moments of its death spiral. The incredible luminosity of a quasar is the light of friction, the death cry of matter being heated to millions of degrees before it is consumed. The efficiency of this process is astonishing. A star, through nuclear fusion, converts about 0.7% of the mass of its fuel into pure energy. An accretion disk around a black hole, through the process of gravitational accretion, can convert 10, 20, or even up to 40% of the mass of its fuel into energy. It is by far the most efficient energy generation mechanism in the entire universe. This is why a quasar, powered by a black hole that is only a few light hours across, can outshine an entire galaxy that is 100,000 light-years across. The accretion disk is not just a source of light. It is a complex and dynamic engine. It is threaded with powerful magnetic fields, which are twisted and amplified by the disk's rapid rotation. And it is this combination, the intense radiation and the powerful magnetic fields, that allows the black hole to launch the two great tools of galactic feedback, the two mechanisms by which it can reach out and sculpt its entire host galaxy. The first of these is a weapon of incredible power and precision, the relativistic jet. The first and most spectacular way that a feeding black hole can project its power across a galaxy is through the creation of relativistic jets. These are two colossal, tightly focused, and oppositely directed beams of plasma that are launched from the poles of the black hole at a significant fraction of the speed of light. They are the most powerful and most energetic sustained phenomena in the entire universe. They are galactic-scale particle cannons. The sight of one of these jets is one of the most awe-inspiring in all of astronomy. We can see them in the radio part of the spectrum, emanating from the centers of active galaxies. They can be incredibly straight and narrow, maintaining their focus over distances of hundreds of thousands, or even millions of light-years. A single jet can be 10 times the size of the host galaxy it is being launched from. It is like a tiny microscopic seed in the center of an apple, sprouting a branch that extends all the way across the room. What could possibly be powerful enough to create such a structure? The engine, we now know, is the accretion disk and the magnetic fields that are threaded through it. As the plasma in the accretion disk swirls around the black hole at near light speed, it drags the magnetic field lines with it. This process twists the magnetic field into a tightly wound helical or corkscrew-like structure that runs perpendicular to the disk. This twisted, rotating magnetic field acts as a colossal particle accelerator. It is a magnetic cannon. It can grab charged particles, like protons and electrons, from the very inner edge of the accretion disk and fling them outwards along the axis of rotation at speeds exceeding 99.9% of the speed of light. The same gravitational forces that are pulling most of the matter into the black hole are, through this magnetic catapult mechanism, launching a small fraction of that matter back out into space with a vengeance. These jets are not just wisps of gas. They are incredibly powerful. A single large jet can carry as much energy as the entire light output of its host galaxy. As this jet plows through the gas of the galaxy and the intergalactic medium beyond it, it creates a powerful shockwave. This shockwave sweeps up the surrounding gas, creating vast, expanding lobes of hot, radio-emitting plasma at the end of the jet. These radio lobes can be millions of light-years across, the largest single coherent structures in the entire universe. The effect of these jets on their host galaxy can be profound and devastating. As the jet punches its way out of the galaxy, it can create a channel or a bubble in the galaxy's interstellar gas, It can heat this gas to millions of degrees, and it can push vast quantities of it out of the galactic disk and into the halo. This is the first great mechanism of black hole feedback. The jet is a weapon that the central black hole can use to attack its own galaxy's fuel supply. The cold gas that would normally be used to form new stars is either heated to the point where it can no longer collapse, or it is physically blown out of the galaxy altogether. A powerful jet can, in a very real sense, sterilize a galaxy, shutting down its star formation and preventing it from growing any larger. We see evidence of this process throughout the universe. In many giant elliptical galaxies, we see vast, X-ray emitting bubbles and cavities that have been carved out of the hot gas by the jets from their central supermassive black holes. This is the direct photographic evidence of the black hole actively sculpting and regulating its environment. The jet is not just a beautiful astronomical curiosity. It is the galactic fountain, the primary tool by which the monster in the middle can reach out and rewrite the destiny of its entire cosmic city. The relativistic jets are the black hole's long-range precision weapons, but the accretion disk itself unleashes another, less focused, but equally powerful mechanism of feedback. This is a one-two punch of powerful winds and intense radiation that can create a galaxy-spanning tsunami, a great blowout that can empty a galaxy of its star-forming gas in a geological blink of an eye. Let's first consider the winds. The accretion disk is not a perfectly well-behaved whirlpool. It is a chaotic, turbulent, and superheated sea of plasma. And just like our own sun, which has a solar wind, the accretion disk has a powerful disk wind. The intense heat and magnetic turbulence in the disk can launch a broad, wide-angle wind of charged particles that flows away from the disk at high speeds, often at about 10% of the speed of light. This is not a gentle breeze. It is a ferocious, galaxy-spanning hurricane. A powerful quasar wind can be carrying away an amount of mass equivalent to our own sun every single year. This wind slams into the interstellar gas of the host galaxy, creating a powerful, expanding shockwave that heats the gas and pushes it outwards. It is like a spherical explosion, a sustained pressure wave emanating from the galactic core. But the wind is only half of the story. The accretion disk is also the most luminous object in the universe, and light itself can exert a physical pressure. This radiation pressure is the same force that pushes a solar sail through space, but on an unbelievably larger scale. The light pouring out of a quasar is so intense that the sheer pressure of the photons is enough to physically push the gas and dust in the galaxy. This combination of the quasar wind and the radiation pressure creates a galaxy-wide superwind, a great blowout that can have a dramatic and decisive effect on the galaxy's evolution. This process is known as quasar mode feedback, and it is thought to be one of the primary ways that a galaxy's star formation can be quenched. Imagine a young, gas-rich galaxy. It is undergoing a furious burst of star formation, a starburst, as its vast reservoirs of cold gas are collapsing to form new stars. A significant portion of this gas is also funneling down to the galactic center, where it begins to feed the central supermassive black hole. The black hole awakens, and the quasar ignites. For a time, both the starburst and the quasar blaze away, but then the quasar's feedback kicks in. The powerful winds and radiation pressure begin to blow outwards, sweeping through the galaxy like a cosmic tsunami. This tsunami slams into the remaining cold gas clouds, the fuel for the starburst. It heats them, disrupts them, and ultimately, it blows them out of the galaxy altogether. In a period of just a few tens of millions of years, the quasar can effectively scour its host galaxy clean of all its star-forming fuel. The starburst is extinguished. The galaxy has been quenched. Its brief, brilliant, and violent youth is over, and it will now settle into a long, quiet, and passive old age as a red and dead elliptical galaxy. We see direct evidence for these great blowouts when we look at distant quasars. We can see the spectral signatures of vast, high-speed outflows of gas, with clouds of material being blasted away from the galactic center at thousands of kilometers per second. This is the direct observational evidence of a galaxy being cleared out by its own central monster. The Great Blowout is the final decisive act in the conversation between a black hole and its host galaxy, the moment when the black hole's power becomes so great that it shuts down the very process of creation that gave it its fuel. We have now assembled the key pieces of our cosmic puzzle. We have the supermassive black hole, a gravitational monster that sits at the heart of its galaxy. We have the accretion disk, the brilliant, violent engine that is ignited when the monster feeds. And we have the two great mechanisms of feedback: the long-range, focused power of the relativistic jets, and the broad, overwhelming force of the quasar winds. Now, we can put these pieces together to understand the beautiful self-regulating feedback loop that governs the coevolution of a galaxy and its black hole. The supermassive black hole is not just a destroyer or a creator, it is the galactic thermostat. Imagine a house with a furnace. The furnace is the galaxy's star formation. The thermostat on the wall is the supermassive black hole. In a young, gas-rich galaxy, the house is cold. There is a vast reservoir of cold gas, the fuel for star formation. The furnace kicks on, and the galaxy undergoes a furious starburst, rapidly converting its cold gas into new stars. This process also funnels some of that cold gas down to the galactic center, which is like the house warming up and that heat signal reaching the thermostat. As the gas reaches the center, it feeds the black hole, and the quasar ignites. The thermostat has now registered that the house is getting too hot. The quasar then unleashes its powerful feedback, the jets and the winds. This is the thermostat sending a signal back to the furnace. This feedback blasts through the galaxy, heating the remaining cold gas and blowing it out of the system. This is equivalent to the thermostat shutting off the furnace. With its fuel supply heated and dispersed, star formation in the galaxy grinds to a halt. In the galaxy is quenched. The quasar, having now cut off its own food supply, also shuts down. The black hole goes dormant. The house is now quiet and warm, and it will slowly begin to cool down over billions of years. This quiescent, red and dead phase is the state of most massive elliptical galaxies in the universe today. But the story may not be over. Over billions of years, the galaxy may acquire a new supply of cold gas, perhaps by merging with a smaller gas-rich dwarf galaxy, or by slowly accreting gas from the intergalactic medium. This is like the house, slowly cooling down again. This new cold gas will once again trigger a new, albeit smaller, burst of star formation, and will once again begin to feed the central black hole. The thermostat will once again register the change. The quasar will briefly flicker back to life, and its feedback will once again heat the gas and shut the process down. This is the great cosmic cycle of black hole feedback. It is a self-regulating loop that perfectly explains the tight m-sigma correlation we see between the mass of a black hole and the mass of its galaxy. The black hole is not allowed to grow too large because its own feedback cuts off its food supply, and the galaxy is not allowed to grow too large because the black hole's feedback sterilizes it. The two are locked in a perfectly balanced coevolutionary dance. This model, which has been developed over the last 2 decades and is now a cornerstone of our modern understanding of galaxy evolution, transforms our view of the black hole. It is no longer a passive sink of matter. It is an active and essential component of the galactic ecosystem. It is the governor, the regulator, the thermostat that ensures that galaxies do not burn through all their fuel too quickly, and that they grow into the beautiful, diverse, and stable structures that we see in the universe today. The monster in the middle is not a monster at all. It is the great and hidden guardian of galactic order. The theory of black hole feedback is a beautiful and elegant one. It perfectly explains the observed properties of galaxies and solves the cosmic chicken and egg problem. But is there any direct observational evidence of this process in action? Can we actually see the scars that a black hole's activity leaves on its host galaxy? The answer is yes, and the evidence is written in a form of light that is invisible to our eyes, in the high-energy glow of X-rays. Our own Milky Way galaxy is at present a relatively quiet place. Our central supermassive black hole, Sagittarius A star, is mostly dormant, but it was not always this way. In 2010, astronomers using the Fermi Gamma Ray Space Telescope discovered 2 colossal, mysterious, and completely unexpected structures emanating from the center of our galaxy. These are the Fermi bubbles. They are 2 gigantic, hourglass-shaped lobes of hot, gamma-ray-emitting gas, extending for 25,000 light-years above and below the galactic plane. They are colossal structures, a testament to a period of incredible violence in our own galaxy's recent past. The most likely explanation for their existence is that they are the remnants of a powerful outburst from Sagittarius A star that happened a few million years ago. Our own black hole was once a powerful quasar, and its jets or winds inflated these 2 giant bubbles. But the evidence becomes even more dramatic when we look at other, more massive galaxies. Let's travel to the heart of the Perseus cluster, a massive galaxy cluster about 240 million light-years away. At the center of this cluster lies the giant elliptical galaxy NGC 1275. This galaxy is filled with a vast diffuse atmosphere of incredibly hot X-ray emitting gas, with temperatures of tens of millions of degrees. For a long time, this hot gas presented a puzzle. It should be radiating away its energy as X-rays and cooling down over time. This cooling should allow the gas to fall to the center of the galaxy and trigger a massive ongoing burst of star formation. But when we look at the Perseus cluster, we see very little star formation. The gas is hot, and it is staying hot. Something is constantly reheating it, preventing it from cooling and forming stars. That something is the supermassive black hole at the galaxy's heart. When astronomers looked at the Perseus cluster with the Chandra X-ray Observatory, they saw a stunning sight. They saw two vast, dark, and perfectly circular voids, or cavities, in the hot X-ray emitting gas, one on either side of the central galaxy. These are X-ray bubbles. These bubbles are the direct photographic evidence of black hole feedback in action. They are being carved out by the powerful relativistic jets being launched by the central supermassive black hole. As the jets plow through the hot gas of the cluster, they push it aside, inflating these giant energetic bubbles. The bubbles are filled with the high-energy particles from the jet, and they are effectively injecting a massive amount of energy into the surrounding gas, keeping it hot and preventing it from cooling. But the Chandra image revealed something even more remarkable. It showed faint, concentric ripples in the gas, spreading out from the central galaxy like the ripples on a pond. These are sound waves. The periodic inflation of the X-ray bubbles by the black hole's jets is creating a series of deep, powerful, and incredibly low-frequency sound waves that are propagating through the entire cluster. In fact, astronomers have calculated that the black hole at the center of the Perseus cluster is emitting a sound wave that corresponds to a note of B-flat, but one that is 57 octaves below middle C. It is the deepest note ever detected in the universe. This is the galactic thermostat in action. The black hole is not just heating the gas with its jets, it is singing to it, sending out waves of acoustic energy that gently and continuously heat the gas over millions of light years, perfectly balancing the cooling process and keeping the galaxy in a state of delicate and beautiful equilibrium. We have now seen the incredible power of a supermassive black hole. We have seen how its jets and winds can act as a galactic thermostat, regulating the growth of its entire host galaxy and creating the beautiful tight correlation between the mass of a black hole and the mass of its stellar bulge. But this grand self-regulating cycle begs a profound and fundamental question of origins. How is the thermostat built in the first place? How does a galaxy acquire a monster with the mass of millions or billions of suns at its heart? The birth of these supermassive black holes is one of the greatest and most active mysteries in all of modern cosmology. For a long time, the leading theory was a simple and patient one. This is the light seed model. It suggests that supermassive black holes start small and grow over time. In the very early universe, the first stars, the so-called population 3 stars, were colossal, hundreds of times the mass of our sun. When these first-generation stars died, they would have collapsed to form the first stellar mass black holes, with masses of perhaps a few dozen or a few hundred times that of our sun. These were the first seeds. In the dense, chaotic environment of a young forming galaxy, these seed black holes would have begun a long and violent process of growth. Pulled by gravity, they would have sunk to the center of the young galaxy's dark matter halo. Here they would have begun to merge with each other, their masses slowly adding up. They would also have begun to accrete the dense primordial gas that was flowing to the galactic center. Over hundreds of millions or even billions of years of these repeated mergers and steady accretion, a small seed black hole could, in theory, slowly and patiently grow into the supermassive monster we see today. This model is a beautiful bottom-up story of cosmic growth, but in recent years, it has run into a significant problem, and that problem is time. As our telescopes, particularly the James Webb Space Telescope, have begun to peer deeper and deeper into the cosmic dawn, they are finding brilliant, fully formed quasars, supermassive black holes, with the mass of a billion suns, actively feeding that were already in place when the universe was less than a billion years old. The light seed model simply does not have enough time to grow a black hole that big, that fast. It is like finding a giant 1,000-year-old sequoia tree in a forest that is only 100 years old. The timeline does not add up. This has led to the rise of a more radical, more dramatic, and more exciting theory. This is the heavy seed model, or the theory of direct collapse black holes. This idea proposes that the universe did not always need to build its monsters patiently, piece by piece. In the rare, perfect conditions of the early universe, it may have had a way to build them all at once. The theory goes like this. In the very early universe, there were some colossal primordial clouds of pure, unpolluted hydrogen and helium gas. These clouds, with the mass of over 100,000 suns, would normally have cooled down and fragmented to form a massive star cluster. But if this cloud was located in a region that was being bathed in the intense ultraviolet radiation from a nearby neighboring galaxy, something special could happen. This radiation would have been just strong enough to destroy the molecular hydrogen in the cloud, which is the primary coolant that allows a gas cloud to fragment. Without its coolant, the cloud could not fragment into smaller pieces. It could not form stars. Instead, the entire colossal 100,000 solar mass cloud would have begun to collapse in its entirety as a single monolithic object. It would have collapsed past the point of forming a superstar, past the point of any nuclear fusion, and it would have collapsed directly and catastrophically into a single massive black hole. It would have skipped the star phase of its life entirely. This would be the birth of a heavy seed, an intermediate mass black hole with a mass of 100,000 suns, was created in a single magnificent event. These heavy seeds would then only need to accrete gas for a relatively short period of time to grow into the billion solar mass quasars that we are now seeing in the early universe. The direct collapse model elegantly solves the timeline problem. The birth of a supermassive black hole is likely a story that involves both of these processes, but the growing evidence from the James Webb Space Telescope, with its discovery of these impossibly large black holes at the cosmic dawn, is a powerful piece of circumstantial evidence that the universe, in its youth, had a way to create its monsters in a single grand and direct act of cosmic creation. The influence of a supermassive black hole is not confined to the luminous borders of its host galaxy. The powerful jets and winds that are launched from its accretion disk are so colossal and so energetic that their effects can be felt on a truly cosmic scale. These galactic fountains can blast their way out of their host galaxy entirely, traveling for millions of light years and fundamentally altering the chemistry and the temperature of the vast diffuse ocean of gas that lies between the galaxies, the intergalactic medium. Black holes are not just galactic architects, they are cosmic web weavers. As we have learned, the universe on its largest scales is structured like a great cosmic web, a network of vast, empty voids, surrounded by sheets and filaments of dark matter and gas. The galaxies themselves form at the densest, nodal points of this web. The vast majority of the universe's normal baryonic matter, however, does not reside in the galaxies themselves. It lies in the tenuous, mostly invisible gas of the intergalactic medium, or IGM, that populates these great cosmic filaments. For a long time, we believed that the only way for this intergalactic gas to be enriched with heavy elements was through the gentle, slow process of galactic winds, driven by the collective effect of millions of supernova explosions within a galaxy. But the powerful outflows from a central supermassive black hole provide a far more efficient and far more violent mechanism for this cosmic enrichment. Imagine a powerful, relativistic jet launched from a quasar at the heart of a young galaxy. This jet, as we have seen, can carve a path clean through its host galaxy, but it does not stop there. It continues to travel for hundreds of thousands or even millions of years, plowing deep into the intergalactic medium of the cosmic filament that the galaxy lives in. This jet is like a colossal cosmic pipeline. It is transporting material that has been processed in the very heart of the galaxy and is now injecting it directly into the primordial, unenriched gas of the IGM. The jet carries with it a powerful magnetic field, seeding the intergalactic medium with the magnetism that may be crucial for the formation of future galaxies. More importantly, it carries with it the heavy elements, the carbon, the oxygen, the iron, that have been forged in the stars of the host galaxy and have been swept up by the jet on its way out. The black hole is therefore acting as a great cosmic polluter, but in the best possible way. It is seeding the universe's great sterile reservoirs of hydrogen and helium with the heavy elements that are the necessary prerequisites for the formation of rocky planets, and ultimately for life itself. The atoms in your body may not have just been forged in a long dead star. They may have been transported across a million light years on a colossal jet launched by a supermassive black hole. But the jets and winds do more than just enrich the IgM, they also heat it. The immense kinetic energy of these outflows is dissipated as thermal energy, heating the tenuous gas and the cosmic filaments to millions of degrees. This heating has a profound regulatory effect on the formation of future galaxies. Just as the black hole's feedback can prevent the gas inside its own galaxy from cooling and forming stars, its outflows can preheat the gas in the intergalactic medium, preventing it from ever being able to cool and collapse to form new small dwarf galaxies in the first place. The supermassive black hole is not just regulating its own home, it is regulating its entire cosmic neighborhood, ensuring that only the most massive dark matter halos are able to accrete gas and form large luminous galaxies. The black hole is a true weaver of the cosmic web. Its influence extends far beyond its own galactic shores. It is an agent of cosmic change on the largest of scales, enriching, heating, and shaping the very substance of the universe. And, in doing so, it helps to create the beautiful, complex, and life-sustaining cosmos that we see around us today. Galaxies are not solitary islands. They are social creatures. Over the course of cosmic time, they grow primarily by colliding and merging with each other. Our own Milky Way is destined to merge with the Andromeda Galaxy in about 4.5 billion years. And when two galaxies merge, so too, eventually, will the two supermassive black holes at their hearts. This final cataclysmic event, the merger of two supermassive black holes, is the most violent and most powerful event in the entire universe. And it is an event that we will not see but hear. The process of a supermassive black hole merger is a slow and majestic dance that unfolds over billions of years. When the two host galaxies first collide, their central black holes are still hundreds of thousands of light years apart. As the two galaxies merge and settle down, a process called dynamical friction begins to take hold. The two black holes, being the most massive objects in the newly merged galaxy, begin to sink towards the center of the new gravity well, transferring their orbital energy to the surrounding stars. After a few billion years, the two black holes will have found each other at the center of the new, larger galaxy. They will form a stable, binary supermassive black hole, orbiting each other at a distance of a few light years. For a long time, this was a theoretical problem. It was unclear how the two black holes could get any closer. The process of dynamical friction becomes inefficient at this scale. This was known as the final parsec problem. We now believe that interactions with individual stars and gas clouds can continue to rob the binary of its orbital energy, causing it to shrink further. Finally, when the two black holes are just a fraction of a light year apart, a new and far more powerful process takes over. They will begin to radiate away their orbital energy in the form of gravitational waves. As we have learned, these are ripples in the fabric of space-time itself. The spiraling binary black hole system is a powerful gravitational wave generator. As they radiate away this energy, their orbit begins to shrink, and it shrinks faster and faster. In the final few years of their dance, they are orbiting each other at a significant fraction of the speed of light. In the final minutes, they are whirling around each other thousands of times per second. The gravitational waves they are emitting are now a titanic, universe-shaking storm. In the final moments before they merge, the binary system is radiating away more energy in the form of gravitational waves than all of the stars in the entire observable universe combined. And then they touch. The two event horizons merge, and in a final violent ringdown, the newly formed, more massive black hole settles into a stable, quiet state. The merger sends out a final, colossal blast of gravitational waves, a cosmic symphony that will travel across the universe for billions of years. We have not yet detected the gravitational waves from a supermassive black hole merger. Our current detectors, like LIGO, are designed to detect the high-frequency waves from the merger of small stellar mass black holes. The waves from a supermassive merger are of a much lower frequency, with wavelengths of millions of kilometers. To detect them, we will need a new kind of observatory, a gravitational wave detector in space. This is the goal of the Laser Interferometer Space Antenna, or LISA, a joint mission between the European Space Agency and NASA, planned for launch in the mid-2030s. LISA will consist of 3 spacecraft, flying in a triangular formation, separated by 2.5 million kilometers. By bouncing lasers between these spacecraft, it will be able to measure the tiny picometer scale changes in their separation caused by a passing low-frequency gravitational wave. LISA will open an entirely new window onto the universe. It will allow us to hear the hidden violent lives of supermassive black holes. We will be able to map their mergers, to test the predictions of general relativity in the most extreme environments, and to understand the final cataclysmic act in the great story of how black holes and galaxies grow and evolve together. We began our journey with a simple image: the black hole as a monster, a silent cosmic destroyer. We end our journey with a new and far more profound understanding. The supermassive black hole is not a monster. It is a partner. It is a vital and perhaps essential component of the great cosmic ecosystem, an architect that works in the darkness to shape and regulate the luminous universe we see. We have seen how the discovery of these titans at the hearts of galaxies led to the profound mystery of the M-sigma relation, the uncanny and beautiful correlation that tells us that a galaxy and its black hole must somehow grow together. We have explored the engine of this connection, the brilliant and violent accretion disk, which can turn a dormant black hole into a quasar, the brightest object in the universe. We have journeyed along the colossal relativistic jets that are launched from this engine, and we have weathered the great galaxy-spanning winds that it unleashes. We have seen how these two forces, born from the black hole's own feeding frenzy, can act as a galactic thermostat, a beautiful self-regulating feedback loop that quenches star formation and dictates the ultimate size and destiny of a galaxy. We have even seen the direct X-ray evidence of this process, the great silent bubbles and the deep cosmic sound waves that a black hole uses to communicate with its home. We have traveled back to the dawn of time to speculate on the birth of these monsters, finding that the universe may have had a way to forge them directly from the collapse of primordial clouds. And we have seen how their influence extends beyond their own galactic shores, as they enrich and shape the very fabric of the cosmic web itself. The story of how black holes shape galaxies is a story of a deep and fundamental symbiosis. It is a cosmic paradox. The same gravitational engine that devours stars and tears apart worlds is also the engine that regulates the birth of new stars and seeds the universe with the elements of life. The forces of creation and destruction are once again revealed to be two sides of the same magnificent coin. To understand the black hole is to understand that our universe is a complex, interconnected, and self-regulating system. The beautiful spiral galaxy we call home is not an accident. Its size, its shape, and its long, stable history of star formation are in part a direct consequence of the quiet, sleeping monster that resides at its heart. The architect of the cosmos, it turns out, works in the dark.